So that was a general overview of how we describe algorithms, how we come up with them, and how we actually write them. And from this point on, we are going to look at the performance of algorithms. And we have mentioned a few results regarding the performance of certain algorithms, like binary search performs better than linear search, or quick sort is quick. Um, so at this point, we are going to try to make sense of what that means. So in general, performance of algorithms are measured with respect to their runtime requirements and their memory requirements. So the first one we call time complexity and the other space complexity. And in the context of this course, we are going to look at only the time complexity. Space complexity is not that different, but you need to actually uh, be, you need to deal with um, data structures and how you represent data in memory. So it requires a little bit more um, information. So we are not going to actually study space complexity in the context of this class. So for instance, let's look at the linear search algorithm, which is provided here. So at best, we need a single comparison. Remember what we were doing. Linear search searches a sequence for a key value. Suppose that you encounter it at the very first trial. That value resides in the first position of the sequence. In this case, you complete the algorithm by doing one single comparison. That's it. And then you exit. But consider the worst case. In the worst case, the value you are looking for is at the very end of your sequence. In this case, you need to execute all these instructions towards the entire, towards the end of the entire loop. So you need to iterate the loop n times actually. So here, what you are doing is to iterate the loop, you need to do a comparison so that you know whether I has reached n yet or not. So there are n comparisons for that, and there are also n comparisons for this comparison here, the whether to see whether you have found the value you are looking for or not. So at the worst case, you do 2 times n comparisons. And of course, these are the best and worst cases. We also have the average case. And in this case, a probabilistic point of view comes into the picture, and we assume every possible sequence is equally likely, and every possible, let's say, key value to be searched is also equally likely. So on the average, assuming data distribution is uniform, we need n comparisons on the average. Okay, so uh, if you have, for instance, n values in your sequence, assuming that the input will be just one of them, the probability of having the first one is 1 over n, and that requires a single comparison, r plus 1 over n probability for the second position, and for that you need to compute I think 3 comparisons. The first, the 2 of them are for this loop, and oh sorry, 1 of them for the loop and 2 of them for this. I mean, it depends on the implementation. It could be that you do 2 comparisons in the loop also. So this could be also 4, depending on the implementation, plus etc. up to 1 over n. And in the worst case, you have 2n. Okay, so this is you see as a sort of expected value. If you define t as the random variable that this program will execute, the duration that this program will execute, let's say, you are doing nothing but an expected value. So you compute this, the average case complexity requires n comparisons on the average. Okay, so best case 1, worst case 2n, average case n. So there are different metrics to indicate the performance of an algorithm. On the other hand, consider binary search. Remember what we are doing. You just look at the middle of your sequence and decide which half you need to discard and which half you need to search your value. So the size of the range is halved after each iteration. So if you start with like 16 numbers, after the first iteration, you will look in 8 numbers. And after the second iteration, you are looking at 4 values. After another iteration, you are looking at 2 values, etc. So the range is halved after each iteration. This means we need log 2 of n comparisons. This is the number of iterations you need, log 2 of n. More precisely, if you actually count the number of operations you need, you will have 2 times log 2 of n comparisons. Okay, one for the advancement of the loop, one for the comparison of the search key. You will need log 2n plus 3 assignments. These 3 are for the initializations of the left indicator, the middle indicator, and the right indicator. And for the assignment of the left or the right, because after each iteration you change either left or right, you are going to need log 2n additions and log 2n divisions divided by 2 because you are looking at the midpoint. So each of these require different numbers of operations, but if you actually look at the algorithm in detail, these are the operations you need to perform. So to be able to compare different algorithms that do the same thing and decide on whether a certain algorithm is better than the other, we need a certain theoretical background, and that will be the so-called growth of functions.